Okay, so let's get started on lecture 10. Any questions before we start this lecture? Okay, new homework has been posted and solutions should be up. Yes?
Last time we talked about jamming, so we can't solve the problem of jamming by putting a filter before the amplifier?
So the question is, can filtering help solve the problem with jamming? Certainly it can help, right? So, let's draw a picture here. So this is my LNA, and I put a sharp filter in front of it, and this is the band of operation. So this filter, this is called a basically RF band filter. But certainly I can now get, this will help with out-of-band jammers, right? But I can have in-band jammers. And as we've talked about throughout this course, in-band jammers are quite common. There are other people sharing the spectrum with you. And the signals that they're transmitting could interfere with the signal that you're trying to receive. So you still have a situation with jamming. Okay. Other question?
Wouldn't that also introduce more noise into the system by putting a filter ahead of the LNA?
Yeah, that's a good point. We haven't talked about noise yet, but we'll find out that actually this does lower the noise figure of the receiver, but it's usually worth it because you don't want to have to deal with a whole spectrum of jammers out there. So at least you limit your spectrum, and that reduces the probability of being jammed. Okay. Any other questions about last lecture? All right. Well, before we move on to feedback, I wanted to introduce you guys to a nice little trick which I'll call end tones in one shot. In other words, if you look at the way we've solved the distortion problem right now, it's kind of been longhand. We've put in one tone, we've taken powers, we've seen that it generated harmonic distortion. Then we put in two tones, and we saw that you can get intermodulation from the second order and third order. I'd like to give you guys the tools to analyze the problem of having m different tones into an, let's say, an arbitrary nonlinearity, or let's say n tones into an mth order nonlinearity. So let me say, let me assume that I want to calculate the output of putting in tones n equals 1 all the way to n and taking the mth power. And we basically want to find out what the amplitude of all the various mixing products are going to be. Okay? So the special case was we solved the problem of one tone, right? We did this one special case. And then we did the one tone with a general power, but for two tones, remember, we only looked at second order, second power, and third power. Now we're going to solve it in general. And the way to do this is to actually write cosine in terms of a complex exponential. And what we're going to do is we're going to simplify this to one sum from minus n to plus n, a n over 2, e to the j omega nt to the mth power. So all I've done was get rid of these terms by lumping them into the sum. Notice that by definition then a0 is equal to 0, and a negative index frequency is a negative frequency with this notation. So for instance, omega minus 1 is the minus omega 1 term. Okay? So I'm just using some notation here, and you'll see that this actually simplifies the problem. Okay? Questions? Yes?
How about the term n equals 0?
Okay, that I get rid of that term by just forcing it, right? So I just say a0 equals 0. Good question. Somebody's awake. Okay, so if you think about this, this is like taking each sum and multiplying it out m times. Okay? And so I can actually write this as, I can take the product of sums and write it as one supersum. Okay, let me come back here. So I'm going to write this as basically a bunch of sums for, let's say, index k1, and I'm going to rename the indices so I can keep track of them, k2, all the way to km, ak1 times ak2, all the way multiplied by akm. I have m of these. And then I have 2 to the mth power times sum, when I multiply exponentials, of course, I can just take the sum of the frequencies, omega k1 plus omega k2, all the way to omega km t. Okay? Is that clear to everybody? Okay, so we're just playing a little mathematical trick, but it gives us a lot of insight. So right away we can see that we generate a complex frequency component, omega k1 plus omega k2 dot 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 omega km. And keep in mind that these k's go from minus n to plus n, right? And when they're minus, you get negative frequencies. So you can see right away that we're getting all these frequency products that we looked at previously. In total, I have actually 2n to the mth terms in this summation, right? Because I have mth power, and there's 2n sums here. So there's a lot of terms adding up here and generating all these various frequency components. What's interesting is that what we can do is actually count the number of times a particular frequency product occurs. So let's see how that happens. Let's take an example to bring this home a little bit. Let me take something simple that we've dealt with. Let me take a cubic nonlinearity and two tones. So this is cubic power two tones. And so my frequencies are omega 1, omega minus 1, and omega 2, omega minus 2, which of course is just minus omega 2. So how many terms do I have? I have 2 to the n m terms. That's 4 to the third power, or 64 terms. So I have 64 complex frequencies appearing. And they're non-distinct. It's important. In other words, they're not 64 different frequencies. A lot of them actually sum up to the same frequency. So what we'd like to do is figure out how many of these frequency components are actually distinct. Okay? So think of it this way. Omega is basically an element of this set. And I can take a whole bunch of different ways and sum these. So because m is equal to 3, I get sum of 3 of these frequencies. So for instance, I can have omega 1 plus omega 1 plus omega 1. That's one of the 64 terms. This, of course, gives rise to HD3. Okay? Likewise, I can have omega 1 plus omega 1 plus omega 2, or 2 omega 1 plus omega 2. This is an IM3 term, right? I can also have omega m plus omega 1 plus omega 1 minus omega 2, right? Because plus omega to the minus 2 gives us the minus sign. So this is 2 omega 1 minus omega 2. This is also an IM3 term that we looked at last lecture. I can also have omega 1 plus omega 1 minus omega 1, right? And that gives me omega 1 again. And we saw last lecture that this led to gain, expansion, or compression. Okay? And so on. So you see you have 64 of these sums. A lot of them sum to the same thing. What we're interested in is distinguishing between these various sums. Okay? Questions? Is it pretty clear? Okay? All right. So we're going to introduce a vector k. Let me call this the frequency mix vector, for lack of a better name. K is going to be a 2n vector that looks like this, as 2 times n elements. And element, so this is a 2n vector, where kj denotes the number of times a particular frequency appears in a given summation. Okay? Now this is a little bit abstract, but once you get the concept of k, it's actually very useful. Let me give an example of what k is. Let's say we're looking at the frequency product omega 2 plus omega 1 minus plus omega 2. Okay? So this is 3 terms. So that means there's actually the vector has 4, the k in this case has 4 elements. And remember, the first element tells you the number of times that frequency minus 2 appears. How many times does the frequency minus 2 appear in this sum? We can just yell out the answer. 0, right? It doesn't appear at all. How about the frequency minus 1? How many times does that appear in this particular sum? 0, right? How about the frequency 1? Yep. And 2? 2. So this is the vector k. Okay? Very simple concept. If you look at another example, you notice that I can reorder this, and I get the same vector. Right? No matter how I reorder these sums, k doesn't really care about the order, And of course, we don't really care about the order. What we care about is the total sum. Okay? Let me do another example just to make sure you guys are awake. So let's do the same thing for this particular product. Omega 1 plus omega 1 minus omega 2. How many terms do we have in the minus 2 column? Right. Minus 1 column. 1 column. And 0. Great. So you guys understand what k is. Well, you'll also notice that for a particular mth order power, if I take the sum of kj, j goes to minus n to n, what do I get? M, exactly. So this is k minus n plus k minus 1, k1, all the way to kn, and that's just has to sum up to m, right? I can't get more than m different frequencies. Okay? I can't get more than m non-distinct frequencies. All right, any questions up to here? So now we'd like to ask the question, for a given k vector, fixed k vector, how many different ways can we form this k vector? Right? So let me write that down. So for a fixed vector, let's say k naught, how many different sum vectors are there? Okay? So this is a little bit of simple counting. So I know that if I have m frequencies, right, I can sum them m factorial ways. But the order is not important, right? So we need to get rid of the order. So each coefficient kj can be ordered kj factorial different ways. So the total number is the multinomial coefficient m factorial. That's the total number that I can sum. And then I have to divide by the various ways I can order. So I can take k minus 1 and sum it this many factorial ways. Right? I can take k1, and for k1, this is the number of ways I can order it all the way to kn. Okay? So this tells me the total number of ways I can build a given k0 vector. Does that make sense to everybody? Questions? Okay. It's too easy. No questions. All right. So also observe that since our signal is real, each term in our sum has a complex conjugate. So hence, there is another vector, let's say k0 prime, that looks like kn, k1, k minus 1, k minus n. In other words, it's flipped around, because the positive frequencies become the negative and the negative become the positive. So if I take this term and its complex conjugate, then I have a real frequency component. Okay? In other words, so if I take the k0 prime and the k prime and I sum them, because they're complex conjugate, I get twice the real part. So I get twice the real part of omega k1 plus omega k2 plus omega km t, which of course is just 2 cosine omega k1, omega k2, omega km t. Okay? And I know exactly how many different sums appear, so the amplitude of any particular frequency component is AM, right? If this is the, if I'm doing a power series, let me not write AM, let me just keep it general. 2 times this coefficient mk, this multinomial coefficient, divided by 2 to the m. This factor 2, of course, just comes from here. So in other words, the amplitude is mk 2 to the m minus 1. Okay? So if I'm interested in the amplitude of a particular, well, this should be k0. If I'm interested in knowing the amplitude of a particular frequency mix, let's say k0, then I just look to see how many different frequency products in those 2n to the m terms add up to give me k0. Well, I can choose, I know, it's very simple mathematics that I can order m things m factorial ways, and I'm not sensitive to the way that I order them, so I just divide by k1 factorial, k2 factorial, k minus 1 factorial, and I have this multinomial coefficient which tells me the number of times I get a particular frequency mix. Okay? 2 to the m comes from taking the mth power, and this minus 1 comes from taking twice the real part. Okay? Now this is actually a very powerful result. It takes a little while for it to sink in. It's good to practice using it. So let's see how we can take advantage of this product. Let me make sure there's no questions about where all this came from. Okay, so let's do some nice examples. Let's start out with something we know. IM3. So let's look at the IM3 products generated by cubic order nonlinearity. Okay? So let's take a particular case. Let's take 2 omega 1 minus omega 2. Okay? This is an IM3 product. Well, first thing we do is we write down the k vector for this particular IM3 product, and I write down my columns here, which tell me which frequencies I'm interested in, and we did this already. This has 2 frequency omega 1 and 1 frequency minus 2. So this is my k vector. Okay? Everybody see where that came from? Yeah, good. Now m is equal to 3 and n is equal to 2 for a two-tone test, right? I should have said that first. So if I take my m, choose k vector, m factorial is 3 factorial, and then I just take the 2 non-zero terms here, 1 factorial and 2 factorial, and I get 3. Okay? And then I also have on my denominator 2 to the m minus 1, so that's 2 squared, or 4. So now I have that the amplitude of this particular IM3 product is 3/4 A3 S input cubed A1 S input, or 3/4 A3 over A1 S input squared. Okay? Okay, so this was an easy problem. We already knew the answer, so it's nice we can derive it another way. Let's do something that would be excruciatingly difficult to derive by hand. So let's do a much harder example. Let me take m is equal to 5, n equals to 1. So just one tone, but 5th order. So you can do it by hand, longhand, right? You can take cosine to the 5th power, or we can use our result. And the observation here is that if I have basically 5 tones, then as long as I get a cancellation, so I have 3 omega 1s and 2 negative, I end up with a net omega 1. So any k vector like this will produce a tone at omega 1, right? So remember, 3 plus 2 is 5. It's a fifth order nonlinearity. And as long as I get 3 omega 1s and 2 minus omega 1s, I get a tone at omega 1. You can, of course, do the complex conjugate, 3, 2, get the same answer, right? Everybody see where this comes from? Okay. And so now if I do m choose k vector, that's 5 factorial divided by 2 factorial, 3 factorial. So that's 5 times 4 divided by 2, or 10. Okay. And then 2 to the m minus 1 is 2 to the 4th, which is 16. Right? So now I can say, let's say I'm interested in the gain, compression, or expansion due to the pentic term. Pentic means x to the 5, right, as opposed to cubic. And I can see that that term will look like a5 10 over 16 s input to the 5th power. Okay? So if I go back and look at the equation I derived last lecture for the apparent gain, last lecture we included the cubic nonlinearity. I'll now add my, so last lecture we found that the cubic nonlinearity adds 3/4 a3 s input squared. And if I take this term and divide it by a1, if I divide this by s input, I get an additional 1016 a5 s input to the 4th. Right? So very, very powerful way of calculating the effect of an arbitrary nonlinearity on arbitrary number of tones. So now I can, on the exam, I can tell you guys m is equal to 7, n is equal to 3, and there's no way you could calculate that by hand unless you use this technique. Okay? Questions? Comments? Yes? Can you use the mic?
How would you get a minus term in this if you were to get gain
Compression? So the sign of A3 and A5 are not known, right? They could be negative. Good point. You'll notice that once you know the sign, the gain, compression, or expansion is independent of the signal level because you're taking even powers.
So, question. If you add the contribution of the complex conjugate, do you multiply the thing by 2, or?
We already did that, right? We already took that into account. That's why we have 2 to the m minus 1. Yeah. All right. Good question. Cool. Okay, so that's just a little trick for you guys. If you don't like this, don't worry about it. You can always do it the other way. Okay? I won't ask you on the test to do 100th order nonlinearity or anything like that. Okay, so we're going to start. Yes, another question.
Previous example, where did A5 come from?
So we're just assuming that you have a power series, right? And there's a term A5 S input to the 5th. And what we're trying to do is count the number of times that that will generate basically fundamental.
Like if this goes like m equal to 5 and say n equal to 3, and you were to find an intermodulation term, like how would you know how many terms would add up, or means we have to do hand permutation to see how it adds up to say 2 omega 1 minus omega 2.
Well, we just did that for this example, right?
So that was for a lower order, m equal to 3. You can find always how.
Yeah. So 5th order, let's say I wanted to do, I can make this negative, right? I could say, let's say I'm interested in, if I put in a 2-tone, let's say I'm interested in 3 omega 2 minus 2 omega 1, right? Well, you just write down the k vector for that. You want to do that example? Okay, we don't have time. Let's move ahead. Okay. Let's do the effect of feedback on distortion. Now, last lecture there was a good question. What once you have distortion, what can you do with it? Well, filtering can help a little bit, but there are certain cases where we see that filtering doesn't help at all. For instance, intermodulation products. And so how do we improve the distortion in such a case? Well, the answer is to use feedback. So let's see why that is. Okay. All right, so let's draw a generic feedback system. Okay, and we're going to use negative feedback, not positive feedback, so I'll put a minus sign there. So this is my input signal, and this is my output signal. Let me call this intermediate signal the error signal, okay? And I know that this block is nonlinear. So let me assume this block is nonlinear, but let me assume that the feedback is linear. And that's usually the case because the feedback is usually like a passive network. Okay? Well, so that means the only nonlinear term is described by this power series. Okay? And I know that my error term is the input minus f times the output. So I can substitute this in here, and I get, expand out all the products. But at the end of the day, I want to write S output as a simple relationship between the input voltage. Okay? So very similar to the way we derived series inversion, what I can do is I can substitute this in here, and then this in here, and equate coefficients. Okay? Okay. So let me try to do that. So I have S output is A1, S input minus SFO, plus A2, S input minus SOF, I keep wanting to say SFO, squared, plus A3, S input minus FSO cubed, and so on. And what I'm going to do is I'm going to substitute this series here. So if I do that, on the left-hand side, I'll have B1 S input plus B2 S input squared plus B3 S input cubed is equal to A1 S input minus FB1 S input minus FB2 S input squared minus FB3 S input cubed plus A2 squared plus A3 cubed, and then we'll stop there. Okay? Any questions about what we're doing? Does it seem clear? Okay, so now we equate coefficients. So let's start out with the linear terms. Okay, on the left-hand side, B1 is the linear term. On the right-hand side, you can see that I have A1 S input 1 minus FB1. Okay, and if I solve this, I have B1 1 plus FA1 is equal to A1, or that finally that B1 is equal to A1 1 plus A1F, or A1 over 1 plus T, which is the loop gain. Okay, this is exactly the result that we get in linear analysis, so it's no surprise. Okay, so now let's do a little search for the nonlinear terms. Okay, so looking here, what nonlinear terms do I have? So on the left-hand side, let's look at the second order terms. So on the left-hand side, that's just B2. On the right-hand side, I have this term here, so that's A1FB2 minus, okay, and then here I have A2, this term squared. So that gives me plus A2 S, let me not write S, canceling out S. And that's it. Everything else gives me a higher order term. Okay? Now let me simplify this a bit. Let me write 1 minus FB1. Well, I know what B1 is. B1 is A1, 1 plus T. So this is really 1 minus T over 1 plus T, which of course is just 1 over 1 plus T. So I have B2, 1 plus T, is equal to A2 over 1 plus T squared. So that B2 is A2 1 plus T cubed. Okay? So we see the effect of the feedback is to reduce second order coefficient by 1 plus the loop gain cubed. Well, that's brilliant, because if we look at what the effect of feedback was on the linear gain, it only reduced the linear gain by 1 plus t. So if I still take the ratio of B2 over B1, I still have an improvement by loop gain squared. So that's really good. Okay. Well, what about the cubic term? Any questions up to here? I should also mention that we're doing this for a memoryless nonlinear system. Often our feedback network will have frequency dependence. Actually, the forward amplifier may also have some frequency dependence. It turns out, if you're careful, in most cases, if you make t as a function of frequency, you still get the right answer. So even if you're looking at a high frequency, as long as you take into account that the loop gain is dropped, you can still substitute here and figure out the effect. Okay. Let's do the cubic terms. I can't spell. Okay, so of course on the left-hand side we just have B3. On the right-hand side, let's look to what we have. Okay, so on the right-hand side, I have this cubic term. So let me write that down. That's A1 FB3 minus. Okay, and then I have another easy one. It's just the first term here, so it's this term cubed. So that's A3 1 minus FB1 cubed. And then I have one more term, which is when I square this thing, it's this term times this term. So I get twice 1 minus FB1 minus FB1. So I get 2 times 1 minus FB1 times FB2, and there's a minus sign. Okay. Let me make sure I didn't make a mistake. Otherwise, you'll be wasting your time. That term looks right. That term looks right. And that term looks right as well. Okay, good. So now what I do is I do a little bit of algebra, and I won't bore you guys. And I solve for B3. And what I get is the following. Okay, so there's some good news and there's a little bit of bad news. The good news is that compared to A3, we can see that by 1 plus loop gain to the 4th power, we get a reduction. The bad news is this term, because this term actually introduces cubic order distortion in a system where you didn't even have it to begin with. This is called the second order interaction term. Remember last lecture we talked about a FET, and we said ideally a long channel FET has no cubic. But if there's any kind of feedback in that FET, for instance, source resistance, shunt feedback through that Miller capacitor, if there's any kind of feedback, which in reality there's going to be, then second order interaction will generate cubic distortion. Okay? So where does second order distortion come from? Okay, anybody? How do we get cubic from second order in a feedback system? Anybody want to venture a guess? Let's look back at our system. Let's say that this only has second order distortion in it. Well, input signal comes in, I have second order distortion, it gets fed back, right? It gets summed with my signal and it goes through again. And so the second order interacts with the first order, and through that square nonlinearity generates cubic distortion. Okay, so that's why we call it second order interaction. Now the good news is that maybe I can use this to actually cancel out my third order, right? After all, there is a minus sign here. So maybe if I'm careful, I can use second order interaction to cancel out my cubic. Turns out that, yeah, you can do this, but it's very sensitive to process parameters, as we'll see for a practical example. But it actually can be done, and it's a good idea if you can somehow do it dynamically. It's a good research topic. Okay. So the observation is I can get basically a cubic null if the numerator here goes to 0, or a3 1 plus t is equal to 2a2 squared f. All right, so now that we've derived these equations, we can basically go in and plug in the results into all the important metrics. So for instance, if I'm interested in second harmonic distortion, well, the equation I derived last couple of lectures where the second harmonic distortion is related to b2 over b1 squared for a given output signal. It's very important that I compare the same output signal, right? And I'll come back to that in a moment. So if I substitute, b2 I found is basically reduced, is a2 reduced by the cube of 1 plus t. And b1, of course, is just reduced by 1 plus t. And so when all is said and done, I have that the distortion output referred is reduced by 1 plus t. Now why is it very important to look at the output referred? Remember, if I compare the input referred distortion, I would get the answer that distortion is reduced by 1 plus t squared. So it's even better. But I don't give myself that pleasure. I use the output referred distortion. Why is that the case? Anybody? You guys shy today?
When it comes to the end of the day, all we care about is the output of our amplifier.
That's
if
a
our
good
output
point.
is shrinked, we might as well HD3 shrink it as well.
Yeah, I think you have it. Basically, we know that feedback reduces the gain of the amplifier. So because of the feedback, I'm going to get less signal at the output. So I might as well compare apples to apples. At the end of the day, I need a certain output signal. So that's why I do output referred HD3. Because if I just do input referred HD3, it's not fair. I can't compare my original amplifier to the one with the feedback because the original amplifier had more gain. I've killed that gain by putting feedback in. But even though I did that, I still have improvement. The output referred HD3 gets better. Okay, very good. All right, so let's look at, that's HD2, let's look at HD3. HD3 we derived last lecture in terms of the output is B3 over B1 cubed output level squared. Okay? And I plug in all the equations that I derived. Again, I won't bore you guys with algebra. And the answer comes out to, I like to write the answer in terms of the distortion of the circuit without feedback times 1 plus t. So great, the distortion level is reduced by 1 plus t, but unfortunately I have second order interaction. So things are a little more complicated. So this is the distortion reduction. Without second order interaction. So what's happening is that the action of the feedback certainly reduces the third harmonic, but it also generates an additional third harmonic. Okay. Now the reason that, just to give you guys a little bit of intuition, the reason why feedback reduces distortion in the first place is, remember, the feedback amplifier is trying to make, remember if we think about it in terms of an op-amp, right? Let me just take a very simple example from as an op-amp. Well, what the op-amp is doing is it's taking the output, subtracting it from the input. It's basically trying to make this input signal very small, right? Ideally, with infinite loop gain, it makes the input signal 0. And so if the input signal is very small, we know you generate less distortion. So that's one way to look at it. Another way to look at it is the feedback system is correcting for the nonlinearity produced by the amplifier, because the feedback system only works with the fundamental. It's comparing the output fundamental with the input fundamental. And any difference is getting rejected. Now that difference could be basically due to the finite gain of the amplifier, or it could be due basically to nonlinearity. So the nonlinearity terms look like extra error terms that the feedback system is trying to get rid of. So that's a little bit of intuition on what's going on. What's interesting, though, is if you now look at the signal that's fed back, you'll find that the signal that's fed back to the input actually has a lot of distortion in it. Right? If I put a pure sine wave inside here, and I look at this node here, you'll find that this node has lots of distortion in it. Whereas here, out here, it's again clean. But let's say that you find that the distortion level here is very small, but if I look over here, I actually might find that the distortion is quite large. Can someone explain what's going on? Can you use the mic?
It's trying to cancel the distortion in the op-amp. So
Exactly.
it's going to introduce the opposite distortion.
Very good. So what's happening is the op-amp internally is generating just the right amount of distortion in order to cancel the distortion that would be introduced by the amplifier. So it's pre-distorting the input. Okay. It's as if you took your nonlinearity, let's say this is a compressive nonlinearity, and you pre-multiply it by an expansive nonlinearity, right? So that the overall transfer function is linear. Well, this expansive nonlinearity is being generated by the op-amp through the action of the feedback. Yes?
But then suppose it were a unity feedback system, then that output point is shorted to the input point. So how can the signals at the 2 points be different?
That's a good question. I'm trying to give you guys intuition, so don't take this as a precise. But this is what's going on internally. Okay. Okay. All right. So what else would we like to talk about? Let me also compare the action of feedback really quickly versus attenuation. Okay. Somebody might say, I don't have to, feedback reduces my gain. So why don't I just come in and attenuate my input by a factor f and look at what happens at the output, right? Because this attenuation makes the signal going in smaller, so therefore I will get less distortion out of this amplifier, and sure, the gain is going to be smaller, but I can choose this attenuation factor, let's call this alpha, so that alpha A is equal to the closed loop gain. So you could say that's an apples for apple comparison, right? Well, I'll let you guys do the math, but you'll find that if I take now the HD2 of this system, output referred, it's exactly the same as the HD2 of this amplifier alone. So it doesn't help, actually. So it's not that you're just attenuating the input. That's why feedback is good. It's better than that. It's attenuating the input and generating the inverse distortion. Okay. And again, notice that I use output referred to do the comparison. All right. Questions or comments?
I mean, even like if this were to give you um, the same advantages as the feedback system, I mean, in reality, I mean, these systems are not perfect, and they have all these problems. Feedback is one thing to correct. I mean,
that's a very good point. So, yeah, just to repeat your point, even if this did have advantages, you still wouldn't want to use it over feedback, because now the whole reason why we use feedback is not just because it improves distortion, but also because it makes our gain insensitive to process and temperature. So feedback has other benefits as well. But you'll note that all those benefits really stem from the same source. So process variation looks like extra error being generated, and the feedback rejects it. Temperature variation looks like an error signal being generated, and the feedback also rejects it. So feedback is good. Okay, so let's do an example of a BJT that we did last lecture, but now with emitter degeneration. Okay. So now I have some resistance RE here, and again, let me drive it with an ideal voltage source Vin, and I'll bias up at VQ. So my input signal is Vin plus VQ, which is equal to VBE plus IERE. Okay, and so I can write this as Vin plus VQ is equal to VBEQ plus small signal VBE plus IQ plus IC times RE. Let's assume that alpha is about 1. Okay? And if I now split this into DC terms, I have that VQ is VBEQ plus IQRE, and then my AC terms look like V input is equal to VBE plus ICRE. Okay? But this is my output signal. Right? So this looks like V input minus ICRE is equal to VBE. In other words, this looks like some error signal is being generated, which is the VBE, which is the input minus some fraction of the output. Okay? So we see that emitter feedback looks like an idealized feedback system where the error signal is little VBE, the output signal is IC, the input signal, of course, is Vin, and the feedback factor is just RE. So emitter degeneration as a feedback system. That means that all the results that we derived last lecture, I can now just, using the results from feedback, just apply. So last lecture we derived that IC is A1 VBE plus A2 VBE squared, where A1 was the GM of the transistor, and then A2 we found to equal to 1/2 IQ over VT squared, where VT is KT over Q. Now we know with feedback, IC is B1 V input plus B2 V input squared, ... And the loop gain, T, which is A1F, is A1 is GM, F is RE, so it's GM-RE. So that my B1 coefficient is A1, which is GM, divided by 1 plus T, which is 1 plus GM-RE. Now that's a no-brainer. We knew that from linear analysis. But what's more interesting is B2. B2, remember, is A2, which is basically IQ divided by VT squared, or multiplied by Q over KT squared, divided by 1 plus loop gain cubed. Okay? So now I can calculate, for instance, directly the HD2 of this amplifier. And I get 1/4 signal swing at the output normalized to IQ divided by 1 plus GM-RE. And if I likewise calculate HD3, you get 1/24 signal swing divided by IQ squared, a little bit messy, 1 minus 3 GM-RE, 1 plus GM-RE, divided by 1 plus GM-RE. Okay? So now we see that the action of the feedback could in fact produce a null if I could get a cancellation here. So let me try to solve for null. That means I want 3 GM-RE to equal to 1 plus GM-RE. In other words, I want RE to be 1/2 GM. So if, in theory, I put an RE, which is basically 1/2 times GM, I'll get no cubic distortion. Now you can see the problem because GM varies as a function of temperature. So if I get perfect distortion cancellation at one temperature, I change the temperature a little bit and RE changes. RE has to change. Of course, it's not going to, so I don't get a distortion null. If I plot HD3 versus RE, I get a plot that looks something like this. Something like that, actually. So this is HD3 on a log scale versus RE on a linear scale. This is the null, 1/2 GM, and this is quite a deep null. So for instance here, I used an example of IQ is 1 milliamp. So for the null, you need about 13 ohms. So if this is 13 ohms, this is something like 20, 40. This here, this level, this goes up. This level here is about minus 50 dB. And so the size of this null is quite large. This is minus 70 dB. So the idea is that if you're here and your resistance changes a lot, you go way up because it's a very deep null, very rapid null. Question?
Can't you do the RE with some kind of a diode connected BJT over there, because then you will get your temperature matching and so on?
That's what people do. Yeah. If you ever look at schematics of op amps and things like that, you see weird diodes hooked up to the emitters, and you wonder, why are they putting diodes in the emitters? Well, that's the answer. Okay, let's look at a BJT with source resistance. So now let's take into the account Rs, which is always present. And so now V input plus VQ minus IBRB is equal to VBE plus IERE. Okay? So if we assume alpha is roughly 1, and beta naught, let's assume, is a constant, and we let RB equal to RS plus little rb, the actual RB of this transistor, then I can write this as V input plus VQ is equal to VBE plus IC RE 1 big RB divided by beta naught. In other words, as you guys know from your basic electronics courses, I can take a resistance and move it over to the emitter by just scaling it by beta, because the currents here, the emitter current and the base current are always, the collector current and the base current are always related by beta. So therefore the emitter current is also related to the base current. So in other words, I can absorb any kind of source resistance and treat it as a feedback resistance in the emitter. Okay? Questions? All right, well, what about an emitter follower? Well, if we look at an emitter follower, this is VQ, this is the input, this is my output. This might be a current source, or this resistance represents the output impedance of that current source. I take my output here. How much distortion does this circuit generate? Well, it's the same as the analysis of RE simply equal to RL. So it's the same as common emitter with degeneration. So in fact, the way we usually build followers is with a current source. And because this degeneration is very large, we see that common emitter amplifiers are actually pretty linear stages. Okay? And that's actually very useful because we use, a lot of times in integrated circuits, we'll use a follower to drive an off-chip voltage, which is typically large. And so the swing is going to be quite large. And so it's good to take advantage of this nice linear stage. So it makes a very good driver, not only because it does the impedance transformation, but also because it's a low distortion driver. Okay? Questions? All right, how about common base amplifier? Well, common base amplifier let me just assume I bias at negative here. So I can ground the base. This is RE and this is RL. This is the input voltage. V input minus VQ plus, assuming alpha is 1, ICRE is equal to minus VBE. So V input, ICRE is in the same direction as V input. This is negative. All this is equal to the minus VBE of the transistor. Well, if you look at this equation, this is of course the same as the common emitter with RE feedback. So here RE might be the resistance you put here. It could be the source resistance of the amplifier. And this actually shows you why a common base typically has better distortion than a common emitter. But what we've shown here is that it's actually the same as a common emitter with degeneration, where the degeneration is the source resistance. Okay. Okay, so now you guys have the tools to analyze all sorts of amplifiers. You can analyze differential pairs. You can analyze differential pairs with feedback. Basically, any amplifier you can dream up, you can analyze with these techniques. These are all single-stage amplifiers. We also taught you guys how to deal with multi-stage amplifiers, so you can use the formulas for cascading, for instance, to generate distortion of a two-stage amplifier or a three-stage amplifier. The only thing we didn't really show you guys is what happens with frequency, right? So everything we've looked at has been what we called memoryless distortion. So the only limit to this approach was that we required memoryless nonlinearity. Now, let's re-examine that assumption. Let's look at a transistor, right? Let me look at a FET and apply a large signal VGS here and what kind of current it generates. Now, what kind of elements inside this FET would generate distortion that has memory in it? Yeah, the capacitors, right? Everything else is memoryless. So I have this small overlap capacitance, right? I have a CGS here. And then I have junction capacitances, right? Now what's interesting is I put this little slash through here to say that this is a nonlinear capacitance. Because this is a reverse bias diode, right? So this is my junction cap. The other capacitors in the system actually look like linear capacitors, right? So you can think of this, if with the exception of this junction capacitance, I can think of this as some linear filter and then some nonlinearity which is memoryless. And then again at the output I have a pole, so I have another filter, let's say. Okay. So it seems like the techniques that we've developed, if we ignore this nonlinear capacitor, can still be applied to even a circuit that has frequency dependence. And in particular, if you're careful, you can just do this by inspection. So for instance, if you have a tuned amplifier, then you know which distortion products are going to get filtered and which ones are not. So if I come in with a two-tone, right, and then I apply it to some memoryless nonlinearity, the output will have third harmonic, right, fifth harmonic, second harmonic, all the intermodulation products. Well, the harmonics will get attenuated by this filter. The intermodulation terms, the ones that fall in band, though, into the pass band of the amplifier will not. Let me just draw a picture for that. So if I have a two-tone, omega 1, omega 2, very close together, and I have basically a matching network, right? Well, we learned in this class that a matching network is just a resonant circuit. So it has some quality factor, it has some passband, and these two tones are going to fall into the passband of this matching network. Then we go into our amplifier, let's say it's a FET, it generates all the distortion products, and then there's another matching network. And that will filter out all the distortion products except for the cubic, pentic, 7th order, 9th order intermod terms with fall in band. The other ones get attenuated by however much the filter attenuates those. Okay. Now how about a BJT? Turns out that a BJT is smarter in more ways than one. It has more memory. Okay? And in this class, we won't really worry about it. It gets pretty nasty to actually handle all that distortion. The memory distortion with memory requires what's called Volterra series analysis. This is something that we teach in 242. But it lets you take into account the memory effects in a bipolar. What are some of the memory effects in a bipolar? Exactly. It's the tau f. It's the diffusion capacitance. You have the nonlinear junction caps just like you do in a MOS, but then you have this diffusion capacitance, which in combination with the junction capacitances makes the device have memory. Okay? Any questions? Okay, we still have some time, so I can just ramble on for a while. So let me just do a recap of what we've learned up to now. So we started out looking at basically broadband amplifiers. So this was really an extension of what we learned in 140. So we looked at basically using feedback, for instance, to make our amplifiers more broadband, and so on. Then what we did was we looked at our amplifier as a two-port, right? And we found that we learned ways of maximizing transducer gain, the power gain, the available gain. We did all those calculations, and we found out that actually if you really care about power, then what you should look at is power gain, and there's ways of maximizing that. And then that really led us to two different concepts. One was resonant circuits. Resonant amps are actually usually called tuned amplifiers, where we used resonant elements to tune out the capacitances in the circuit, and also to matching networks, which let us transform the source and load impedance to a more optimal value to try to maximize the power gain. So you can see that here, this is really stuff we've learned in 142, because we're looking at the limits of performance. What's the best power gain we can get out of a transistor? What if I put feedback around it? What if I use matching networks? Then what we did is we looked at distortion. Because, in other words, we looked at the large signal behavior of a device. And this is important because you never actually have infinitesimally small signals going into your amplifier, right? Linear analysis strictly only holds for very, very small signals. We always have signals with some finite amplitude. And no matter how small they are, we see that they generate distortion, right? So the past few lectures have been really looking at how these nonlinearities produce distortion in our amplifier. What we're going to do, starting with next lecture, is we're going to look at noise. Okay? And if you like, if I have a given amplifier, I can think of it in multiple dimensions. I can think of the power gain, right? I can think of its bandwidth. I can think about its distortion. And to complete the picture, I really need noise, because the noise tells me the smallest signals that I can process with an amplifier. So noise sets the limit for the smallest signals that can be processed by the amplifier. Okay? In other words, if I hook up, if I actually take the output of my amplifier and look at it on a spectrum analyzer, okay? A spectrum analyzer, if very rough way to look at it, is plotting how much power is in a given frequency band, okay? So you can think of a spectrum analyzer as taking the output of the amplifier, applying a very narrow filter, bandpass filter, let's say with sub-hertz kind of resolution, and then going into a power detector and then plotting the results. So if I plot the results of the output of my amplifier on a spectrum analyzer, let's say I put in a signal, cosine omega 1t A naught, it gets amplified, right? So it's going to be GV A naught cosine omega naught t. So in the spectrum, I'll see a tone which corresponds to this signal getting amplified. But what I also see is noise. So even though there's no input energy in these frequencies, it looks like there's broadband noise. We call this white noise because it's flat. It has